Hello and welcome to this introduction to Optum G3. I am going to basically solve a very simple problem that we have an analytical solution for, namely the bearing capacity of a circular foundation on clay on a Tresca type material, and I'm going to play around with the material a little bit and also compare the solutions with a program that doesn't give analytical as in closed form solutions, but which is known to give very accurate solutions for this special case of a circular footing, namely the program ABC by Chris Martin from the University of Oxford. But we'll get to that in a little while. So a circular foundation, and I'm going to model 1/4 of it, and I am going to do that by first basically creating the soil domain. So I'm going to use the box tool up here and then create a box. I might make it something like 10 by 10 and then 5 meters high. So that's my soil, and I'm going to place 1/4 of the foundation here. So these two planes here, this plane and this one over here, will be symmetry planes. And to model the foundation, I am going to use a so-called N prism. That's this tool up here, which is a discrete cylinder comprising n sides, where n is a user-defined parameter. And in this example, I'm going to set n to 40, so that we have 10 sides on 1/4 of the cylinder. And the center of the cylinder is here, and then the radius, I might make that something like, say, 2, and then a height of 1 meter. So we have now the soil, and then we have the whole foundation, but we want to get rid of 3/4 of it. You'll notice as well here that the intersection between the foundation and the soil domain has been automatically recognized. So if I unselect solid, so I'm only able to, I select everything with this setting. If I unselect solid, then you'll see that an intersection has been automatically created here between this cylinder or N prism and the soil domain. So you can do this selection on-off of solids, faces, lines and points down here as well. So I need to get rid of 3/4 of the cylinder, and the easiest way to do that is to do it using this automatic intersection. So draw another box here, and from out here and up here, and then we can start deleting. Use the delete here. You can also just use the delete button on the keyboard. So here we have it, a 1/4 of the total problem, the soil domain and the foundation. So that's the geometry, and then we move to materials, and I said we wanted to first consider a Tresca type soil, and that's exactly what we're going to do. So as in G2, select the solid that you want to apply the material to, and then press material, the Tresca material. These are the default parameters. It has an SU of 100 kPa and then a unit weight. It doesn't really matter for this example, but it's 18 kilonewton per cubic meter. And we can edit these, we can change these parameters as we like, but we might just leave them as they are. And then for the footing, we apply a rigid material, also completely analogous to G2. Has a unit weight of 0. So this is what we sometimes refer to as an academic foundation. We will keep things like this for the purpose of comparing with exact or very accurate solutions. So we then need to apply, first of all, some boundary conditions, some supports, and the standard fixities. Again, analogous to G2, it applies normal fixities on these planes here, and the bottom of the domain is fully fixed. To rotate this geometry, you press Control on the keyboard and then use the mouse basically to rotate it. And then load, and we unselect surface here, and then we can apply a multiplier distributed load to the top surface up here. It looks like a line load, but if you zoom in you see that it is actually a distributed load with an intensity of 1 in the Z direction. That's actually the local Z direction here. The coordinate system that we're using now is the local one, so the blue local here corresponds to the blue global in the sense that it's the local Z coordinate. We can change to global coordinates as well in this case. It doesn't make any difference. So -1 in the Z direction. And I just need to plug in some power here. And so that's basically it. And then as in G2 we have the stage manager, the different analysis types, and we'll stick with limit analysis. And we have some settings associated with this analysis type, with this stage, namely the element type and the number of elements. And then do we want mesh adaptivity? We'll say yes to that. And then we have 3 different element types in Optim G3, lower, upper, and mixed. So the lower and upper give lower and upper bounds on the exact solution, and the mixed element is an interesting element in that it tends to give something that is very close to the exact solution. It can be proven that it always gives something that's in between the upper and lower bounds. And of course this is the land in which the exact solution lives. So it gives very accurate results, even for a fairly low number of elements, especially if you combine it with mesh adaptivity. So, but we'll try to use all 3 element types in this example. So the lower, and then I'm going to clone the stage, switch to upper, and then a 3rd stage where we're going to use this mixed element. So let me just rename the stages: LB, lower bound, UB, and mixed. And then I'm ready to run the analysis, and that's what I'm going to do here. So the results are in, and we started by computing the lower bound, 578.4, upper bound 660.5, and then the mixed result 616.1. And to compare with the exact solution in this case would be about 605. We could also compute it using this. It's a well-known analytical solution, but we can verify that using this program ABC, which is a program that's based on the so-called method of characteristics. So it's not a finite element program, and it has limited capability. It applies to strip and circular surface foundations. So it's limited in its capability, but it's very quick and very accurate for these special cases that it's able to handle. So C0, that's in this case the SU, and the unit weight, again, doesn't really matter, but let's just put in what we have. It's a circular foundation. It was rough. It had a width of 4 meters, so a half width of 2 meters. There was no surcharge, and then you press auto guess, press trial mesh, and then you press adjust mesh, and then you can double up a couple of times to get to something that is really very close to the exact solution, 604.8. So let's see what we have. We consider this the exact solution. I'm going to switch to my favorite calculator, MATLAB. I'm going to call the exact solution E. Then we had a lower bound, we'll call that L. An upper bound, I just want to calculate the error here, U. and the mixed element, we can call that M. And then we can calculate another quantity we can call A, namely the average between the upper and lower bounds. So that average often tends to be really quite close to the exact solution. We know that from 2D, and it's the same in 3D. So 6, 19, and note the mixed element 6, 16, it's actually a little bit better. But the mixed element tends to give something that is very close, or which is sort of close to the average between the upper and lower bounds for the same types, same kinds of meshes, same number of elements and adaptivity steps and so on. So it's in a way a shortcut to obtaining this quantity, this average between the upper and lower bounds, which I think is well known and well recognized to really in most cases be quite close to the exact solution. In this case the mixed element is a little bit better, but if we calculate the error, so say the error between the exact solution and the upper bound, so upper bound minus the exact divided by the exact times 100%, something like 9%. The lower bound, lower bound minus 4.4%, so the lower bound is actually a bit better in this case. This average solution about 2%, and the mixed element slightly better, 1.8 or 1.9% error. So pretty accurate solutions for this what is a relatively coarse mesh, 1,000 elements and 3 adaptivity steps. The solution looks like this. You can see it looks as expected, and as the shear dissipation, basically the shear stress times the shear strain at failure, that looks something like that, and you can see the sort of expected failure mechanisms or regions of plasticity. So everything is as expected. Now we could make things a little more complex by considering a linear variation of strength with depth. That's of course something we often see, and that's sort of an important thing to be able to consider, and we can do that fairly easily in Optim G3. So I clone this stage. I'm just going to switch to the mixed element only from now on. So clone this stage, and then the material we're going to use, I'm going to create basically a copy of the Tresca basic material that I've used so far. I might change just the color of that. Let's make it green like that. And then I am going to have not a constant SU, but an SU that varies with depth. So we could say that we first need to record the coordinate up here, the Z coordinate, that's 5 for this point here, the top surface up here, and then we are basically ready to change the parameter here. So you click the field, the SU field, and then you will see a calculator symbol that opens the calculator. So that might be useful for other purposes. In this case, we want to get to the P, that stands for parameter, and where you're able to basically specify a gradient. So the value is the value at the reference Z coordinate, that's 5, and we might use a value of say 10 kPa, and then a gradient of we could say minus 3 kPa per meter. Okay, so and I'm not going to run these again. Okay, I changed the Tresca material instead of the material I just created. Well, never mind. So I changed actually this material here rather than this one. So we can delete this one again. Good. So let's run. and the result 72, collapse multiplier 72, which should be multiplied onto the reference load of 1, so a bearing capacity of 72.4 kPa for this footing here. And let's look at how deformations look. They look very similar to what we had in the previous case. You can plot the SU as well, just to be sure that you're actually doing the right thing. So you can see a linear variation from 10 up here to 25, so a gradient of 3. So 5 meters times 3 is 15, plus 10 is 25. And if we switch to ABC, well, then the C naught up here should be the 10. The K is the gradient without a minus on it, and the unit weight and everything else is the same. And let's see what we get. So we get 70.9, and we have 72.43 here. Again, we can calculate the error just for the sake of completion. Let's open the log again and copy this. And it was this, and there should be a minus there. So an error of 2%. Again, not bad at all. Now sometimes we would like to have some surcharge, and we can have that as well. So we'll have some load up here, and that would be a fixed distributed load, again analogous to G2, and the idea is in the limit analysis it's only the multiplier loads that are actually factored. The fixed loads remain at whatever value you set it to. So let's have that as 10 kPa, and then let's try to solve again. And meanwhile I'm going to do the same in ABC, so set it to surcharge to 10, and then trial mesh and adjust that a couple of times. Yes, so that increases the bearing capacity by 10 kPa. So that's not really too surprising, and we get exactly the same as we had before, plus 10. So same kind of error, a couple of percent, a little less than 2%. And the failure mechanism like that. Let's clone this again, and let's try to switch to a more challenging case, namely a sand. So that is a more Coulomb material. We have these example materials. So for example, a loose sand MC, that's again as in G3. So here we have a friction angle of 30 degrees, a unit weight of 16. And let's try to then solve this problem. And again, let's try to set it up in ABC. So it was 13 and then 16 for the unit weight. And the other parameters are the same. So yes, ABC obviously is faster. But yeah, well, not that much actually. It's a great program for verifying these types of solutions. And the result is in 962. ABC gives 1022. What does that correspond to in terms of error? Again, not very much, slightly more than before I think, but it's also a slightly more challenging example. Purely frictional materials, so zero cohesion, these are more challenging problems. So 5.9%. Not bad at all, and of course with more elements you would get even closer to the exact solution. Let's see how that looks. It looks something like this. We have these huge deformations here around the edge of the foundation. And the shear dissipation, yes. So the mechanism has a greater extent. Maybe we should have even extended the domain a little bit. That's actually fairly easy to do. And what you simply do is you go back to geometry, and then we want to basically drag these edges out, so to make the domain a little bit longer. So untick the solid again, and then press this move. So select this face and then move, and then select some sort of base point and then out to here, and the same for this side. So it's fairly easy to extend the domain, which is of course something that's kind of often required. Yeah, and I think that actually, well, yeah, so that gives more or less the same as before. More or less the same as before. And the domain is definitely large enough now. Again, of course, more elements would give an even more accurate solution. So I think that concludes this simple example dealing with circular foundations. There'll be more examples available online. So see you next time. Bye.